Okay, let's unpack this. We are diving into a whirlwind week for NVIDIA.
Right at the very end of the year, too.
Exactly, the final stretch of 2025, specifically December 21st through the 28th. And this was not a holiday break for them. It was a period of intense, multi-front focus.
It really was, aimed squarely at what feels like the next phase of AI.
Low latency inference and, fully autonomous agents.
And what's fascinating here is seeing how the hardware and the software strategies just converge perfectly. You get this definitive architectural blueprint for the Blackwell B200 chip,
Right.
confirming its bias toward inference efficiency, and then at the same time, this massive strategic licensing deal.
The Groq deal.
The Groq deal.
Yeah.
It signals that consolidating their lead in inference is now, without a doubt, the top corporate priority, even over raw training power.
Exactly. So our mission for this deep dive is to synthesize the core intelligence from the stack of sources shared by you, our listener. We're covering the AI research, the hardware that drives it, and the strategic deals that are, well, securing NVIDIA's ecosystem.
From the cloud all the way down to a single thread.
Let's start with the research. We saw the unveiling of the Nemotron 3 family of models. This includes the Nano, Super, and Ultra variants. The big headline here from their arXiv paper is this new kind of hybrid model architecture.
This is a major efficiency play. They're combining mixture of experts.
Which you can kind of think of as giving the model a bunch of specialized brains.
That's a great way to put it. They combine that with a Mamba-Transformer architecture, and that's important because traditional transformer models, they hit this quadratic wall.
Every time you double the context, the cost just quadruples.
Making long context incredibly expensive. So the Nemotron 3 Nano variant addresses this by swapping out those expensive self-attention layers for Mamba 2 layers.
And what does that trade-off actually buy them in performance?
It buys them linear scaling. Mamba 2 is a state space model, so its cost scales linearly with sequence length, not quadratically.
Which means they can practically support context lengths up to 1 million tokens.
And deliver 3.3 times higher throughput compared to a similar transformer MoE. It moves long context from just a cool technical feat to, a production reality.
But they didn't stop there. For the bigger models, the Nemotron 3 Super and Ultra, they introduced something else called latent MoE.
Right.
This feels like a direct attack on memory and communication bottlenecks.
It is. Latent MoE is a really novel technique. It's designed to optimize the communication cost between those expert brains we talked about.
So normally when you route data to an expert, it's a pretty large package.
It is. The token embedding is a big piece of data. What latent MoE does is it projects that large token embedding into a much smaller latent space before it sends it.
So instead of shipping a 4K video file across the data center every time, you compress it to 1080p first, route it, and then upscale it.
That is a perfect analogy. It dramatically reduces the communication payload, the memory costs, and that allows them to scale up the total number of experts.
Which improves the model quality.
Exactly, without incurring these huge latency penalties. And what's really critical is that this software innovation perfectly foreshadows the specialized compression hardware we're going to see in Blackwell. It's all one unified strategy.
And this theoretical efficiency, it translates directly into enterprise value. We saw that in the Nemo 4 PayPal Commerce Agent case study. How did they turn this into a business win?
Well, the research showed the power of these domain-specific models. PayPal fine-tuned a Nemotron small language model, an SLM, just for their commerce agent.
Okay.
And they found that the search component was taking up over half of the agent's total response time. It was a huge bottleneck. By optimizing that SLM, they just resolved it.
And that's where the metric hits the bottom line.
The result was a 49% reduction in overall agent latency.
Wow.
And a 45% cut in GPU operational costs. In e-commerce, that kind of speed directly translates to more revenue and, of course, lower spending.
So it confirms this idea that massive general-purpose models are for training, but specialized, fine-tuned, smaller models are the answer for production inference.
At scale, yes. They're often the most effective and cost-efficient solution.
Okay, so we've seen the models get more efficient. Now let's look at how the tools are accelerating the development itself. The barrier to writing high-performance CUD kernels has, it's always been intimidating.
Oh, yeah. Deep C++ expertise was basically a requirement.
But that seems to be changing with the latest CUD-Ake's release.
This is a huge democratization move for low-level GPU programming. CUTLASS version 4.3.4 graduated the Qt domain-specific language, or DSL, out of its beta.
And Qt is a Python native interface.
Right. which means developers can write these incredibly high-performance CDA kernels without ever leaving Python.
And the release notes mention orders of magnitude faster compile times. It flattens the learning curve and speeds up iteration so much.
It lets researchers focus on the AI innovation, not the C++ memory management details.
And if you're actually deploying one of those Nemotron models, you need TensorRT-LLM to get every last bit of performance out of it.
The flagship inference framework, absolutely.
And we saw the pre-release candidate, version 1.2.0 RC6, drop this week, which shows just how aggressive that development pace is.
And this tool is essential because it enables optimizations like speculative decoding.
Which is?
It's a really clever technique where the GPU predicts and processes future tokens before the model has even officially confirmed them. Well, it's speculating.
And that can give you up to a 3 times throughput boost on NVIDIA GPUs.
Exactly. It's a key part of supporting these low-latency agentic techniques we've been talking about.
Now, all that is data center focus. We can't ignore the consumer side. The gaming ecosystem is still key, and GeForce NW saw a big holiday content update.
It's a brilliant showcase. 13 new titles. It reinforces the whole value proposition.
In what way?
GeForce now demonstrates that NVIDIA's latest consumer GPUs, like the RTX 5080, can be delivered globally, on demand, from the cloud. It strengthens the link between their core AI infrastructure and that premium consumer experience.
Right, so we've seen how the software side is getting optimized, but none of that matters without the silicon. Let's dig into the B200 blueprint that makes this low-latency push possible.
Okay.
The analysis confirmed a radical shift in how the B200 handles its matrix operations.
A massive shift. Hopper, the previous generation, required all 32 threads in a warp to synchronize before executing these matrix multiply accumulate operations. That's the WGMA instruction.
A choke point.
A huge choke point. Blackwell just eliminates it. The new instruction, TCUJAN05.MILMAA, is thread independent. Threads can execute their operations without waiting on their neighbors.
In simple terms, they just got rid of the traffic lights.
That's a great way to put it. For an inference pipeline where one layer's result immediately feeds the next, reducing that synchronization overhead is everything.
So what's the performance gain?
Removing that barrier achieves anywhere from nearly 3 times to over 11 times lower single instruction latency compared to Hopper. It's a massive deal for the kind of fast, sequential decision-making that autonomous agents require.
And they also introduced specific memory innovations to support this, namely Tensor Memory TMEM and a hardware decompression engine.
Right. TMM is basically a dedicated high-speed loading dock for tensor data right next to the processing core. It's a 256 kilobyte on-chip memory per streaming multiprocessor.
And that cuts down latency in cache-miss scenarios by 58%. A big speed bump for the most critical data.
A huge one. And the decompression engine, the DE, that ties directly back to what we were saying about Nemotron 3.
Ah, right. The compressed models.
Precisely. The hardware decompression engine achieves this exceptional output throughput, over 460 gigabytes per second, for compressed formats like Bitcomp.
So you can store your model weights in a highly compressed, much smaller form, and you don't suffer a performance hit when you need to actually read them.
It tackles the memory bottleneck from both ends. Speed up the access and shrink the data being accessed.
Shifting gears a bit, infrastructure isn't just about silicon. It's also about global access. And there was some news on H200 shipments to China.
A significant policy event. NVIDIA informed its Chinese customers that it intends to start shipping the H200 before mid-February 2026.
And this is a much, much more powerful chip than what was allowed before.
Oh, yeah. It's roughly 6 times more powerful than the H20, which was the previous restricted chip for China. So even with a 25% tariff, that policy reversal unlocks a tremendous amount of demand.
It just shows the incredible commercial pressure to satisfy that market.
On the manufacturing side, though, we saw a clear focus on predictability.
The news about Intel's 18A process.
Exactly. NVIDIA discontinued testing it for its next-gen chips.
Now, halting testing on Intel, that seems like a big failure for supply chain diversification. Aren't they putting all their eggs in the TSMC basket?
It definitely increases their concentration risk, yes. But the decision highlights their priority right now: speed and certainty of delivery for Blackwell.
So they're choosing stability over diversification.
For now, yes. By focusing entirely on their existing partner, TSMC, they ensure faster delivery and avoid potential delays from a new, unproven process like 18A. Speed is the priority.
All right, let's talk about the single biggest strategic shockwave of the week.
The Groq deal.
$20 billion, just an incredible number, To license technology and acquire key talent from a competitor known for ultra-low latency.
It is an explicit confirmation that AI inference speed is now the hill. NVIDIA is willing to spend its immense resources to own. Groq had this highly deterministic, incredibly low-latency architecture with its language processing unit, their LPU.
It was a real threat.
It was arguably the most potent, pure inference threat to NVIDIA's dominance.
So why structure it as a non-exclusive licensing deal for $20 billion instead of just a full acquisition?
Well, by doing it this way, they secure the core technology, they integrate key talent, like the founder Jonathan Ross, but they do it without navigating all the regulatory headaches and antitrust scrutiny a full acquisition would bring.
So they neutralize a competitor, secure the IP, and reinforce their position as the integrated leader, all in one move.
A very, very expensive, but very strategic move.
And finally, let's zoom out from the data center to some foundational science. This application of so-called physical AI. We saw some fascinating research from the Marine Biological Laboratory.
This is a great example of where AI intersects with fundamental biology. Researchers there used NVIDIA RTX GPUs and custom AI tools plus a VR platform to process and visualize 10 terabytes of 3D microscopy data.
10 terabytes of 3D brain data from hippocampal neurons.
Visualized in VR with AI assistance. It's a key application of this physical AI initiative. It shows how accelerated computing can speed up the study of these fundamental puzzles, like how memory is physically encoded in the brain.
Which has real potential for breakthroughs in treating things like Alzheimer's. So when you put it all together, what does this all mean for you? The sources we covered this week, they present a single, unified, aggressive strategy.
You have the hybrid architecture, like Nemotron 3's Mamba-Transformer MoE.
Combined with hardware optimization like Blackwell's TMM and its decompression engine, it's all aimed at delivering speed and efficiency for this new era of autonomous agents.
And that massive $20 billion Groq deal, it just confirms that inference speed is the highest priority. They're not just building the best chips, they are spending historic sums to acquire the best intellectual property to solidify that lead.
So let's leave you with a provocative thought.
We spent some time on how Blackwell's hardware decompression engine and its new FP4 support are optimized for these highly compressed model weights.
Right.
And analyses have shown that running a model like Mistral 7B in FP4 delivered a 2.5 times throughput speedup. A huge gain, but it came at a cost. An 8.2% quality degradation, which is measured by perplexity.
And just a quick definition check. Perplexity is basically how confused the model is. A lower number means higher quality.
Precisely. So the question for you is this. How soon will the market prioritize operational cost savings and speed over that final 8% of quality? When does it become standard to make that trade-off?
Effectively making these highly compressed, specialized models the default for every single application, accepting a small quality hit for massive gains in efficiency.
It's a fundamental trade-off that's going to define enterprise AI deployment over the next year. You have to consider the implications of all these moves from research labs to the cloud that powers global commerce.
That's it for this deep dive.